So
Okay.
welcome Manuel Serra and Nuno Duarte on the talk, NVIDIA ISAC Lab. Welcome both of you.
Yes. Just a second for me. I will join with another computer to share the slides. Okay. Okay. So I think you can see, sorry. I hope the presentation works well. So, hi, nice to meet you all. My name is Manuel. I'm a PhD student at VisLab and IST. Today I want to present you a tool that I've been using during my studies. It's called Isaac Gym, and it is a simulator that is done thinking about reinforcement learning. And it is special because it runs on GPU, and this is what I will talk to you about. And then at some point during the presentation, Nuno Duarte will take over. We'll present a little bit more details on one project that we are using this simulator for. And then in the end, if we have time, we will try to get a robot moving that's here to my right and show you. But that part, we will see if we get there. Okay, so what's the motivation for using simulators? So it's robot learning because, you know, when you are in a factory, so you have seen a lot of robots. It's not anything new. But the problem is that in those environments where it's very common to have robots nowadays, you can usually program everything beforehand and then just repeat the same program every time with very precise and repetitive movements. So this works very well, and it's obviously super useful. But there are situations where we would like to have our robots in uncontrolled environments where we cannot repeat everything the same every time because some things are unpredictable. For example, if we want to teach our robots how to walk, you're going to have irregular terrains, and there will be wind, there will be unexpected things happening around the robot. Or if you want to teach the robot to manipulate some objects, like picking up or stacking something, it might be faced with objects that it never saw before that you cannot program for, or it doesn't know the weight of the object that it needs to pick up. So we cannot really write a program that accounts for all of these unforeseen possibilities in open environments. So yeah, so if we want to teach something like this to a robot, that he can walk in uneven terrains and climb stuff, what we have to do is find a better approach, and that is to have the robot learning how to solve the task. So we don't write a program; we just allow it to learn. So one tool for doing this that's very good for robotics is reinforcement learning. There's other types of learning, but this one is a special one because it is in part comes from inspiration about human infants, and also because it learns by trying stuff and then seeing if it works or if it doesn't. So usually the reinforcement learning environment requires you to have an agent, which is in this case your robot, and the robot is observing the world around it. That's what we call the environment. And then, conditioned on what he just observed, he will choose an action. He will apply that action, and it will change the environment in which he is situated, and then he will see if it was a good action or a bad action, and that's what the reward tells him. So it's like a dog. When he behaves well, you get a cookie, but if you don't, maybe you will shout at the dog. So what we then tell the robot is that he should be choosing actions that maximize the expected reward over time. So if he does this a lot of times, if he tries and fails and sees the reward, eventually he will become very good at the task that he's trying to learn. So this is a very general formulation. It's why a lot of people have been using it. So you have seen applications in robotics, but also in video games, and in health for protein discovery and other things, and even more recently in generative AI. But okay, so I really like reinforcement learning, but I also know that it has very big problems. And these ones are, so the first one that I would like to mention is that it requires a lot of interactions. So this usually is thousands or millions of attempts at different actions until it starts finding what are the best actions to solve a task. And the other problem is that at the start, the robot is just moving around, and it can do dangerous things. And so it is very dangerous to apply this in a robot in the real world, because that's expensive equipment. You don't want it to break. And so you cannot be doing actions that are just trying and failing. You need to be certain that it will work when you work with a real robot. So instead of applying this in the real world, what we do is we replace the environment with a simulator, and then we have the robot learn inside the simulator. And when it's good enough, then we can transfer the behavior that the robot learned to the real world. And this is what we will try to show today. Okay, now a little bit about simulators. We have this diagram that I had before, but up until a few years ago, simulation was quite slow, especially learning and reinforcement learning in simulation. So why is that? A learning algorithm usually is running inside a GPU. That's your typical deep learning optimization happens there, because that's where it's most optimal. It's the fastest. But traditional simulators were designed and were programmed to run on CPU. This is for historical reasons. And what that meant is that you had this workflow that was split on two sides, because they don't share memory. You would do an update in your learning algorithm, and then you would have to transfer the data to the CPU, in this case, the actions, to the CPU to get the next state in the environment inside the simulator. And then again, back the other way to the GPU for the next step. And so this is, as you can imagine, very inefficient, because there will be just the data transfer is a lot slower because it has to go through the PCIe bus. So this is, I calculate, about 20 times slower than if everything was happening in the GPU and you had everything in the same memory. And then also because you have to coordinate a lot. So sometimes what can happen is one of the sides is waiting for the other to finish. And that generates idle times that make everything just run very slow. And then one last disadvantage is that the simulation in the CPU, you can parallelize some things but a CPU doesn't have the same parallelization ability that a GPU has. So you are losing possibly some things you could take advantage there. So these older simulators, what you would see would be a single robot interacting. Here is a simple environment, just a cube and a sphere, but it will be just one robot, and it's a little bit slow. So um, simulators that you have that use this type of workflow are Mujoku, which actually is changing since last year, Gazebo and PyBullet. So yes, but then this is the fun part. Enters Isaac Gym, which was developed by NVIDIA, and NVIDIA makes GPUs, as you all know. So they don't want to be using CPUs. They want everyone to buy GPUs. So they make these tools that run on their GPUs. And so you don't need the CPU anymore. Now everything when you use Isaac Gym just runs inside this unit and uses the same memory. So all of these arrows transferring observations and actions and rewards back and forth are much faster because you are on an end-to-end GPU pipeline. This also allows very good integration with PyTorch, which is a nice to have for someone that's programming. And I will show you in the next slide something that's very nice is that it allows massive parallel environments. So now you will not have just one environment. And then this simulator, so most simulators do the last bullet point, but it provides you with rich physics. So you can have rigid bodies, soft bodies. You can simulate the contact dynamics, the gravity, the forces, everything. So it provides a lot of tools. So as I told you, now you don't have one single robot. You can define environments where you have thousands. Here I put 16,000 robots trying stuff and learning at the same time. And this, of course, depends on the amount of memory you have. But so this is what Isaac Gym allows you to do. But yeah, so you might be wondering then how you start because it seems nice. You want to try, and it's actually pretty simple. So of course you need to have one GPU, but it doesn't have to be a very good one. Even if it's a few years old, you can still use it. And then there is this repository which is called Isaac Gym Envs, which is a companion to Isaac Gym. And they give you already a lot of environments that you can start from. So these are examples of things that you can just run that program and it will start learning. And so they have a lot of diversity there. So you have robotic arms, you have robotic hands like the Shadow and the Allegro hand. You have quadruped robots, and this is just the ones that come with this package. But actually, if you search the web, you will find other types of robots and of things that people have shared on GitHub, for example. And then it also has different types of tasks. So, for example, for quadrupeds, it's very geared towards locomotion. But with arms, they have different types of object manipulation, pick and placing, stacking, and manipulating cubes inside the hand. So if any of you wants to start, what I would do is just pick one of these examples and then start playing with it, changing things and so on. It's pretty easy. But to be a little bit more specific, I will show here some snippets of code and what it usually looks like to work with this simulator. So the interface is with Python, although in the background I think it's written in C. The first thing you have to do is define an environment. So in this case, just going to this back slide, I will be showing from this environment with this arm stacking 2 cubes. So the first thing is you need to define the robot, which is usually done with this URDF file. It's a universal robot description file, which basically just defines the joints, the limits of the robot, and then also adds the meshes for the visualization and the collisions. And then you set the options, so you can say that the base of the robot is fixed, if it feels gravity or not. So you have a lot of parameters here that you can change. And then you also choose the starting position of the robot. And some other properties. One that I highlight here is how the joints are controlled for the robot. So you can have position control or effort control. But then you don't want to have just the robot. You also want to, in this case, have other objects. So we define a table, which is where the robot is interacting with the environment, and 2 cubes. So he will try to put cube A on top of cube B. And then this is the special part about Isaac Gym, is it's not just one environment. Then you create them inside a loop. So here you can have 1,000, 10,000, whatever your GPU can fit. So I usually go as high as possible. Okay, then the second step in preparing a workflow for Isaac Gym is to define how the robot moves. So in this function, the prephysics step, you receive the actions that come from the learning algorithm. So, and then you will take these actions, you will make the necessary computations with them. For example, you will enforce joint limits so that the robot doesn't do unrealistic movements. If you are using torque control, then you will, in this case, in this example they were using, they have this function that converts. And then in the end, you will send the final commands to the simulated robot. So these last 2 lines send the command for the gripper of the robot and for the arm joints. And as you can see, they are using different types of control, which is also possible. Then you have to define the things that were part of that earlier diagram, the observations, the rewards, and the rewards. So in this case, for this robot, the observations can be the positions of both the joints and the cubes. So you just go here, you have these data structures where you keep updating where each cube is, in this example, of course, and where the gripper of the robot is, and so on. But you can also have, as part of the observation, which is not in this example, contacts if the robot is touching anything. And you can have cameras, even though if you have cameras, everything gets a lot slower because then the amount of data multiplied by the number of environments explodes a little bit. Okay, then in step 4, you have to define the reward function, which is also part of what I was showing there. So you can have multiple terms, and you can also apply logic inside the reward function. So in this case, because the example I chose is a robot stacking a cube, the first thing that they reward is that the distance between the hand of the robot and the cube A should be as low as possible. So they have this function that measures this metric. And then you have another reward when you start lifting the first cube. So that means that probably you are close enough, and now you are touching. And if you actually lift the cube, it will start work. It will get some reward. But then you don't want to just lift the rewards. You also to lift the cube. Sorry, you want it to be on top of the other cube. So they have this function that will check if the two cubes are aligned. So if they are aligned, I think they are taking probably the vertical axis. Then that means that they are probably on top of each other. And you can have different weights. And then, yeah, so in the final rewards, they just combine everything together. Okay, and then I have here also this bullet point, which is important and is usually part of this function is when do you start again? Because reinforcement learning is episodic, so you have a fixed number of time steps, and then you start again from the initial position for a new attempt. And that's also important for learning. You can say that if the cube goes to the ground, then the episode starts again, or if the robot collides with the table, you also start again. Okay. Then, okay, this part I don't have. I will just. You also have to create some config files where you define you choose some parameters. You tweak how you can tweak the architecture and so on. But this is not important for now. But then the thing that's very cool is that you don't have to worry about the learning algorithm, the optimization, and you also don't have to worry about how the physics are handled. So everything is in the background. You just interface with these simple functions that I showed you, and you can start training. So this video that I have here was just I don't know, maybe not even 1 hour of training. So it's pretty cool. Okay, so this concludes the first part. I will now hand over to Nuno. You can take my screen away if you want. I will stop sharing.
Okay, thank you. Thank you, Manuel. So let me share my screen. So can you see my screen?
Yes, yes.
You can? Okay, good. Okay, so thanks. So since you have this overview from Manuel about how useful simulators are, and especially this breakthrough of having GPU-based simulators where we can speed up tremendously the training, and we can try as many environments as many tasks as possible. So it adds tremendous value and tremendous potential use cases. So I'm going to show you a very interesting problem that just to give you guys some inspiration of what can be possible to do in reinforcement learning and what can be a potential very advantageous solution to be applied in the real world. So Manuel talked about some of the environments for some toy examples. This one is a much more concrete example. It's something very dear to us and very important, which is on restoring the past. So there's archaeologists that work all their life uncovering and discovering ruins and ancient cities and ancient historical sites where there's a lot to take out of underground. So there's a lot of excavation, a lot of meticulous and laborious work that involves taking out these ancient and priceless artifacts. But out of all this very let's say heroic work, there's not a lot of people that are willing to devote their lives for uncovering and not only excavating but carefully taking out of the ground, but also storing them in warehouses and cataloging, labeling, and trying to piece them together. There's not a lot of people, and usually this work takes months, years, even decades to complete. So this is where robotics can come in hand and assist and work together side by side with humans to hopefully speed up these probably generations of work into work that could be 10x or 100x accelerated. So out of these excavations, there's one in particular that is very interesting to us, which is fresco puzzles, so fresco paintings. So this is very common in the Roman Empire, where houses and monuments and important buildings, they will be decorated. Their walls, their ceilings. Not sure if you went to Rome, or into the Vatican, and you've seen the St. Peter's Cathedral. Their walls and their ceilings are magically painted by these amazing painters. These are fresco paintings, and they're of course they're in perfect shape, those, but there's thousands and thousands of them that are being discovered at this very time, at this very moment. And unfortunately, because of erosion, because of natural disasters, they are being discovered, and they're fragmented. They're a bit scratched. They're a bit sensitive, and they're not a complete piece. Archaeologists are finding very scattered pieces. So robotics here, the challenge would be to use robotics to help archaeologists to how to complete these puzzles that archaeologists would take hundreds of years to complete, because these are thousands and thousands of pieces. And so not only helping on building the puzzle, so the strategy, how to construct, where each piece goes, but also to have a helping hand, so another robotic arms to grasp and handle these objects. So let me next slide. So the biggest challenge, one of the biggest challenges, the most interesting to us, is the fragility of these fragments. So here's an image of an archaeologist handling these pieces. So he's being very careful. He's trying to avoid touching the surface, because that's where the painting is, and that's the most sensitive part. But the whole piece is very prone to degradation and to breaking into even smaller pieces. So you have to be very careful on how you handle this. So we can use reinforcement learning, and we can use these simulators to, instead of using robots first, having robots in the archaeological sites, starting to already handle these pieces, which is completely um, out of the question, because we don't want to risk any of these fragments to get destroyed. We can first start in simulation, and recreating these fragments in simulation first, in order to have in order to I'm sorry, in order to try to learn how to better handle these fragments, and avoid any accidental breakage and accidental falls. So this is our approach for this project and for this challenge. So we are using the Isaac GM environment. We are putting our robot in this environment. We are using rendered versions of these fragments, because there's a plethora of already pieces that are already scanned by archaeologists, but are still not yet constructed. And we have these scans, these 3D renders, and we put them in our simulator, and teach the robot how to better handle these, how to grasp carefully without applying too much force, without touching the surface, and without dropping, without any risk of damaging the real Frescos. So first we go for the first policy in RL policy, which is to pick and place, which involves using a 5-finger hand instead of a gripper. So most of the robots that you see, it's using a gripper, but we think it's more in line with how archaeologists works to use a 5-finger hand similar to a human hand, because we want to be inspired, and we want to follow the guidelines and how archaeologists do it. We want the robot to help and work just as a human would handle these pieces. So the hand we chose, we could have gone to a fully actuated hand, but we went with a 1 degree of freedom hand that I'll show briefly what I'm talking about. This is called the QB hand. It's a hand proposed by an Italian company, and it's tendon driven. So tendon driven in the sense that each finger tries to mimic the tendons of the human finger. So this is what I'm trying to explain what type of hand we are doing. This is the QB hand. It has 1 degree of freedom, so it only opens and closes. But since it's tendon driven and it's semi-rigid, you can have many configurations of the hand, even though you only have 1 degree to control it. This is really nice, because, like Manuel showed before, in the reinforcement learning, you have the observation space, so what the robot sees, but also the action space. So how much degrees of freedom you are using to control. It's okay. It's okay. Sorry, we're having another presentation at the same time. It's a bit distracting. Sorry about that. So we are using this hand because it has only 1 degree of freedom, but it can mimic the human behavior very well. And the fact that it has only 1 degree of freedom, it reduces our action space. So we have a robotic arm that has 7 degrees of freedom. It can do many configurations, and then we have this hand which has only 1 degree of freedom. So this still so it can mimic the human grasping, but at the same time save us a lot of trial and error, because if it was a fully dexterous hand with multiple degrees of freedom, the RL would spend a lot more time trying to explore each configuration of the hand, and we are not interested in that. We're interested in having human-like behavior to handle the pieces like like the human would handle. So this is more or less our pipeline. So we try to create this environment to be as realistic as the real one. So our robot tries to be as comparable to the real robot. The hand, the same way. We want the hand to be as real to be controlled as realistically as our real hand. And then, of course, we run reinforcement learning with trial and error, multiple times, multiple environments, multiple configurations of where the pieces is, or where the pieces should go, of how the arm could be configured, so the policy can learn how to adapt to multiple locations of the objects, multiple target locations, and multiple sizes of the objects, because we're going to have a plethora of different fragments. And we want the robot to generalize to as many pieces as possible, and not to just overfit on how to grasp just one type of fragments. So this is why then we do policy refinement to shape the reward after grasping, to then how to best transport the piece, and then how to precisely and carefully drop the piece without dropping it at the high distance. So we won't. When you transfer this to the real world, you won't fragment the piece. So we want to reduce we want to reduce the risk to the fullest. So we want the real environment to take into account to all the different dangerous and the knots to do in the real case. So I'll show you briefly here a demo of what we've been doing, the multiple case, the multiple policies. We have here many environments. We're showing here already a learned policy that learns to pick one fragment. The fragment can be anywhere in the table, and then it learns to carefully drop the fragment as close as possible to the table without breaking it. And also the target is also being varied all around the table. So after many trials and errors, and after many constraints, we are able to gather something that works quite nice in simulation, and we'll try to show you how this works in the real robot. So then the second part is that we want to build the puzzle, and we want the puzzle to be complete, like an archaeologist would do it. But the robot has the limitations. So the robot when he has to release the object, he has to have space to open the hands and safely step out of the table. So we cannot place objects too close to each other, because this would lead to accidental touches and accidental possible scratches to the fragments that are already in the completed location. So then we try to place them in a safe distance, and then we want to slightly then push the pieces together side by side to avoid any as little contact as possible, but this will allow us to complete the puzzle. So again, we go through the same process. We create the environment, but first we wanted to make it try and work in a more simplistic. So we wanted to disregard the fragment, but first try in a more primitive geometries like cubes, because the idea is to first see if the policy can learn the pushing motion and how to handle using a 1 degree of freedom semi-rigid hand, how to handle the physical collisions and the dynamics of touching cubes in order to push them, but not to push them in a way that they would flip, and not to push them too hard on the surface. So all these constraints to try and mimic how a fragment will be, but first we're focusing on the actual pushing motion. Of course, then after this is complete, we then move on to fragments, and then of course if this works really well in simulation, we then try to adapt to the real scenario. So I'll show you a video of what I'm referring to. So imagine this is a setup where we have one blue cube that is already in its ideal position, and we want to put this green cube into the target location, which is on this red sphere, and we want this cube to be inside that red target and with a certain orientation. And then we have this environment where there's only the hand, and the reason for it is because we are assuming that we already found a nice configuration for the arm, and the only thing we want is the pushing motion and how the hand interacts with the objects. So we exclude the arm because we assume that we know how to move the arm, but the trickiest part is the dynamics interaction between the cubes and the hands, and that's what reinforcement learning can be very useful and help us a lot. This is more or less the assembly process of how to achieve our goal, is to place the fragments with a safety margin in their correct locations, and then we plan how to build where the pieces should go, and then we do the precise pushing to move the pieces to its correct locations, and then we verify if everything is according to plan. So this is a very interesting problem that reinforcement learning could really helps us to achieve this in a very reliable way, and with avoiding many of the dangers of working with real robots, not only to the danger of the robot, but also the danger of the objects. So we can avoid any potential dangers, and try to create a policy that follows all the guidelines that we intend. So if we have some time left, we would like to show you our demo of the pick and plates. That is the video that I showed. We already have a really nice reel to sim transfer, and this is thanks to the fact that we put a lot of effort in our simulator to mimic the robot kinematics and also the hand kinematics as well. And I know if whenever you're ready, Manel, we can show the video. But this ends my presentation. Thanks a lot for listening. So let me stop sharing, and let's see if we can be successful in our experiment.
Okay. Can you mute?
So I don't know if you. Yes.
Okay. So now I will take over again, and we will try. As I said in the beginning, we train in simulation to have safe environments and for it to be faster. But in the end, we want to test things in the real robots. So now we will try to show you. This is what we are currently doing. So please don't grill us if it doesn't work. But nevertheless, we're gonna do our best. So first, I will just show you it working without the robot moving, because I want to show you the cameras. Okay, let me share the screen again. Okay. Okay, so this is our code for this task. I have modified some things compared to the previous example I showed. So now we have this block, which is for getting the position of the objects from a camera. So we are using Aruco markers that gives us the position and the orientation. And then I have another block that's different. Well, a few more things, but this is the main differences, which is telling it if I turn this on, then the real robot will move, which is a Kinova arm, and also the hand will move, which is the hand that Nuno talked to you about, the under-actuated one. So right now I will just show an example with the detection from the camera, but not the arm moving, just only in simulation. Now, because this is a test time, we are only using one environment, so you will see only one robot in the simulator. But during training, we had a lot of them. It takes a few seconds to launch. Sometimes it fails, so let's hope this is not one of those times. Okay, so here you can see this is the simulator, and here you have the fragment with the position, which is being fed to the simulator. And then we also have markers in the tables, so that then we can compute a transformation between the position of the fragment and the base of the robot, which is what the simulator wants to know. Okay, so now I will close this one and relaunch it. But now this time with the robot moving, I think you can see Nuno is filming with his cell phone. I don't know if you can see. Maybe you have to click Nuno's Nuno Duarte. Yeah, you have to click his camera. So I will stop sharing so that you can see better what he's filming. Wait, how do I stop? Okay, stop sharing. Now, if you click on Nuno Duarte, you can probably see better while I launch the code again. I have to do a couple changes. Okay. So we are a bit nervous because live demos sometimes don't work, but let's see. And sorry for the noise. There is also another visit in parallel with this workshop. This just takes a few seconds. Sorry for the wait. You have to be patient because it's fast, but there's also always a few seconds of wait in the beginning. And okay, I think it's about to start now. Okay, so the detection didn't see the fragment. So I will move it a little bit and try again. And maybe we do one more try, and if it doesn't work, maybe we can share a video in the end. Okay. Sorry for the delay. Okay. It is now moving. So in the simulator, as you saw, the robot was picking up the Fresco. Now it's basically imitating what he was doing in the simulation. So one issue we have had is that the robot is a bit higher in the real world, and so sometimes it cannot grasp. Let's see if this is a successful attempt. Okay. It failed, but this is, it's a work in progress. But now in the simulation, he actually succeeded. So he's completing the movement and he was releasing the fresco. So I think it will not work better than this today. But nevertheless, thank you for being patient. And yeah, maybe if it works, we can we can share a video with all of you when it's working better. And yeah, this concludes our presentation. If you have any questions, please, we'd like to answer.
Thank you very much. Very, very interesting session. And thank you for the demo and simulator as well. And yeah, I will ask the audience to come forward for the questions. Yes, we.
Uh, okay, I have two separate questions for Professor Manuel and Professor Nuno, one each. My first question is for Professor Manuel. So, on the sixth page of your of your presentation, I didn't really catch the architecture, the workflow that you were trying to showcase. So, there's a robot with a GPU, and there's a simulator with a CPU. I didn't really understand what was the workflow between going on between these two entities.
Yeah. So I will share the slides again. Just a second. Sorry to show you that. Okay. One moment. Okay. So I think you are referring to this part here.
Yes, that one.
Right?
Yes.
Yeah, so this is how other simulators used to work. So Isaac Gym is special because everything happens in the GPU, but other simulators, they have the learning algorithm running in the GPU. That's the reinforcement learning. So it's reinforcement learning nowadays also uses deep learning in the background. So you have to optimize and do computations. You have to do a backward pass and a forward pass. That all of that is much more efficient inside a GPU. So that part we always want to run in a GPU. But the problem is that the physics simulation, so when the robot chooses an action, applies that action in the environment and sees what changes, that is simulated inside the CPU for these other ones, not for Isaac. And so the issue with that is that you have data transfer overhead. So every time you need to send the action from the GPU memory to the CPU memory. So you have different RAM memories for each. And then the simulation advances one step in time, and the new state of the simulation is sent back to the learning algorithm, which is living inside the GPU. So you always have this happening thousands and thousands of times per second. But the problem is that it's slower to do it like this because sometimes one of the sides is waiting for the other one to finish. And also because having everything just in one is much faster because you eliminate the data transfer. Sorry for the noise. And so that's why we use Isaac Gym is because everything lives inside the GPU, both the learning and the simulation, and that's why it's much faster, and that's why you can do these with thousands of robots just because the GPU is more powerful for parallelization. I don't know if that clarified.
Yeah. So if I understood it correctly, for every one instance of change in the GPU, the CPU inside simulator had to undergo 10,000 to 10,000 different iterations just to keep up with the GPU's clock speed and the runtime, right?
Yes, that's
And
it. That's what
and with
happened.
ISA, yeah, so and with ISAC Gym, the RL agent entity and the simulator entity are now inside the GPU's environment, and they're able to keep up with each other. Like they're able to synchronize
Yeah.
with each other. Yes. Okay.
Yes.
Yeah. And my second question is to Professor Nuno. So generally, whenever we see various monuments from the time of the Sumerians all the way to the present, we know that over many periods, over the centuries, there would have been fragility, there would have been molds. And while I do acknowledge the fact that this robot, that QB hand, which you used to ensure the monument's fragile entities are picked up without any issues, have you ever faced any shortcomings whenever you ran different iterations on it?
I'm sorry, if I faced what?
Have you ever came across any shortcomings and what mitigations you took to overcome it?
Because by using the dexterous hand instead of what? By using the
Uh,
hand, you mean?
yes, yes.
Okay. If I faced any shortcomings. Well, I mean, there's multiple manipulators you can use for sure. The reason why we chose this one is because the degrees of freedom it allows you can mimic most, if not all, human configurations for manipulating objects. And that's really nice because we were trying to get inspired and trying to learn also from how humans grasp these fragments. Since we know from experience that there's only a certain way that we should grasp these pieces in order to prevent any deterioration and any scratching. We grasp in this particular motion that this hand can achieve quite fast. So if we use grippers, this is not possible because the only way a gripper could grasp this piece if it had a big enough wide area. And then this would be extremely dangerous for not only for the robot but also for the piece because the approach of the robot will be to come
Yeah.
in contact
Yes.
and there's potential dangerous. There's also other types of manipulators like suction cups. We could have used a suction cup, but this involves touching the surface, right? And this surface is where the painting is, and the painting is very sensitive to scratches and to losing its color, its natural color. So we want to avoid actually putting any rubber material and constant suction cups to prevent this. And there's of course other dexterous manipulators we can use that has more degrees of freedom. These ones, uh, the more degrees of freedom you have, the more rigid the hand is, and the more rigid, the more potential risks it comes with, because it's a harder material coming into contact. And this hand is everything else is it's being worn. It's a rubber glove. You don't have any motors in the fingers. It's all tendons. So everything is very malleable. So it's nice. It has these properties that are nice properties to come in contact with a piece and not put a lot of force and impact onto it. So it's a trade-off, right? You could have more degree of freedom and more flexibility, but it could lead to other situations. Or you can go to completely soft, like suction cups, or even like, I don't know, these blobs that just engulf the fresco. But then there comes with other drawbacks, which is that you don't know what's going to happen to the surface, and you want to
Yeah.
once again, this is also should be approved by the archaeologists, and they don't want the surface of the where the painting is to come in to be worn out, right? So it's a balance that we have to work with.
Yeah. While you mentioned about archaeologists, I suddenly remembered something. What is the one key factor that distinguishes your project from the nominal excavation and restoration projects that archaeologists all around the world usually take? Uh,
But this distinguishes ours from
yes,
other
yes.
jobs, from other works.
No, no.
Well,
What distinguishes your project from the excavation expeditions that various archaeologists take whenever they go to certain historical sites across the world?
mhm.
That is one.
Well, these are, I mean, using robotics alongside humans it's a very recent topic of exploration. So archaeologists have been working for many generations on these historical sites, but robots don't usually have never been to these sites, because it's still a topic of research, right? And there's still lots of work that has to come into. Our robot will not go to the excavation parts. It helps the robot in the where from of handling the pieces that already are taken from these sites and go to warehouses. So the pieces are already cleaned and they were cleaned and it's extracted, but there's still lots of work that needs to be done, which is to scan them, catalog them, look at the surface, see the patterns, see where this piece fits with the rest. This is so to reconstruct the puzzles, and of course moving the pieces around to their respective location. This is work that so archaeologists, they have to choose, right? Should we go and excavate more pieces, or do we go and study the pieces that we already have, right? So there's robotics can help in many ways, but we are focusing more on the part of the scanning, the reconstructing the puzzles, and the manipulating the pieces that already are in the warehouses.
Okay, I don't have any more questions. Thank
Thank
you.
you.
Yeah, thank you very much. Yeah, thank you very much, Manuel and Nuno, once again.
Yeah.
Thank
you for
Yeah.
your time as well.
Yeah, on behalf
Yes,
of
thank you, Matilde.
yeah, hi Nuno, great to see you.
Nice to see you again. Yes.
Yeah. Yeah. On behalf of the Department of Computational Intelligence and SRMIST, it's my honor to deliver the vote of thanks for this truly insightful session on Nao and Isaac Jim. A heartfelt thank you to our speaker, Laura, Manuel, and Nuno, for your expertise and engaging presentation that have provided us with a fresh perspective and wealth of new information. The way you broke down complex concepts such as choreograph implementation, Isaac Jim, repository, example workflow, and the simulation, even this Fresco puzzle assembly simulation live demo, all were exemplary and has left us with something new to think about. A big gratitude to Professor Jose Santos Victor and Professor Alexandre Bernardino for arranging such a fabulous team for expert talks from BISLAB and facilitate academic international collaboration. This was such an informative and insightful event, which I'm truly very sure that which will lead to many more new research ideas and collaborative worklets in the future. All the sessions are recorded and I will share them with you at the earliest. As the head of the department mentioned yesterday, Professor Jose, I also take this opportunity to welcome you in person to visit our campus in the upcoming years. Thank you very much once again, all of you, and I'll share all the videos too.
Thank you very much to
Thank you, Atira.
and to all. It has been very inspiring. Very inspiring. Thank you so much.
Yeah. So today it was like this. I like the flow because in the morning also we have been talking about how the choreograph software being used, and now in the afternoon session we could see how it is used for some real world applications, especially some high risk scenarios, very critical scenarios, as in medical field. So it's a food for thought. We have a lot of ideas now to collaborate. I think it will be nice if we could give some small worklets with this team of students who attended the workshop. We can develop some small modules and we can have the exchange of knowledge and some small projects and research ideas, right? Yeah.
Very
So
good.
can also take it to the chair. Yeah, we also host GPU. Since you were mentioning about this GPU powered simulators, Isaac Jim, we have this DGX 100 machine in the department, and it would be really great if you could make use of the full potential and use it towards this kind of high-end robotic platforms, right? So sir is also working on the grasping related robotic applications. We have Nirio, similar to KUKA, the Nirio platform, and he's planning to bring the tactiles also into that.
So we are now working on with tactile sensing as well as vision-based grasping. So to grasp with different objects and with different intensities. So I want to go for grasping of fragile objects, how I want to grasp that one. So these kind of things that we are currently working on it. So as ma'am said, we'll keep working on it and then we can send you what we
some small proposals we can make, some 2 or 3 small proposal for the worklets, and we will keep in touch and we will see how we can realize into real world projects and some collaborative work. Yeah.
Sounds very interesting. Yes, this will be a great opportunity.
Fantastic. Thanks a lot again. It was really very inspiring.
Thank you. Thank you.
Yes, I hope you enjoyed the whole workshop. And sorry for the failed attempt, but this is real demos, real life demos. It's always the
no worries.
there's always the
yeah, we were actually
but we are all
it's so realistic, the way it was moving, the fingers and all, very realistic it is. Yeah, more to learn.
Yeah, the movement is completely following how the RL policy was trained in simulation. Now it's just a part of tweaking the environment to match what the robot was used to seeing. That's the most challenging, is to replicate.
Yeah, and also it's interesting to see how you are connecting it with your valuable treasures, your the Fresco patterns, right? We in India also we have a lot of cultural activities that we can do, make use of this kind of vision and AI, which are not really happening, but these are really small hints where we can connect the dots and think something for future. We are also interested to pick up something of that sort. We know
this is really nice to combine the human part and the robot part into getting to a team that can achieve greater things, especially recovering the past, restoring the past. It's a great motto.
That also indigenous things like you are doing. very specific to the place. Whatever you are doing, the Fresco puzzle, right?
Yes, exactly. We first go to the site and we talk to experts, and then we try to what's the best way and how to adapt robotics to what they need, what their goals and desires.
Exactly.
It's not the robotics. It's not them adapting to it. It's not them adapting to the robot. It's the robot having to adapt to the needs.
Nice, great.
Okay.
You see how I'm feeling that this is a really application point of view. Because generally we learn with the robotics and we do it one by one. But as of seeing your examples, we got still more insights. So how we can still develop and do with the works. Thank you so much for this kind of presentation, sir.
Of course. I'm looking forward to share knowledge and collaborate more.
Yeah,
Thank you
very much. I'll read out.
Thank you, everybody.
Message. Okay, thank you very much, and
Thank you.
we'll keep in touch. And bye bye, all of you.
Bye.
Yeah, with this we will
Thank
wind
you.
up
Thank you.
the session, and thank you all. Yeah, thank you very much.
Thank you very much.
Thank you,
It was
everyone.
great.
Bye bye.
Thank you.
Thank you.
Thank you.
Ciao.